Okay, let's go ahead and get started. So just an announcement, I have here a graded first problem set to pick up, along with a solution set. Your second problem set should be graded and ready to pick up soon. Your third problem set is due on Wednesday. I have copies of it here if you haven't already picked up a copy of the problem set. Okay, so today, as promised, I'm going to finish our discussion of the basics of quantum dynamics. So today, I'm going to review what is known as the WKB approximation, at least here in North America. The ordering of the initials and the addition of other initials in the WKB approximation depends greatly on exactly where you are. In some places, it's the BKW approximation in whatever B's country was. Sometimes there are other letters that are added to it, depending on who is getting credit for it. Just for my information, my understanding is that most of you have seen the WKB approximation before. So for that reason, I'm going to go a little more quickly than I might otherwise. How many of you have seen the derivation of the Bohr quantization rule using the WKB approximation? Did you guys raise your hand if you've seen that? Not too many. Okay, good. So we're still going to have fun stuff to do today, and I'm sure we're also going to do things that you haven't seen too. Okay, good stuff. So what we've learned so far in this class is that one can learn a great deal of intuition about quantum mechanics by understanding as precisely as possible how our classical notions of dynamics arise from quantum dynamics in the limit where we think of h bar as being very small. And the most precise version of that reasoning occurs today when we discuss the WKB approximation. So let me just first consider a very simple example. Let's consider a particle moving in one dimension. So what I would like to do is determine the energy eigenstates of the system. That is to say, I would like to find the eigenvalues of the Hamiltonian operator, which in the position space basis is just our friend, the second order differential operator involving the sum of d by dx squared and b. Thank you. Actually, would you mind closing the door? Thank you. So let me rewrite this formula in a slightly more suggestive form. So let me rewrite this as d by dx squared plus 1 over h bar squared p squared acting on psi is equal to 0, where p squared is just found by solving this equation, by rewriting this equation up above. And you can see with just a moment's thought that that's going to be 2m times the square root, times e minus v. So that p, which is the square root of 2m times e minus v. And if we think about that expression for a minute in classical mechanics, so the energy of a classical particle is the sum of the kinetic and potential energies. So E minus V is the kinetic energy, 1 over 2 times mv squared. And so this, in fact, is nothing more or nothing less than the classical momentum of a particle. So in our semiclassical limit, this particular combination of E and V should play the role of the classical momentum. And we've written Schrödinger's equation in a suggestive form in this second line here, involving this expression which we identify as the classical momentum. Okay, now for the approximation. So let's consider the case. So let's rewrite our formula for the Schrödinger equation. And instead of working in terms of the wave function phi, let me work in terms of the log of the wave function. Instead of working in terms of the wave function psi, let me work in terms of the log of the wave function. which I will call phi, and then I will assume that phi is of order 1 and expand Schrödinger's equation in powers of h bar. So that the leading term in the h bar going to 0 limit will give some equation of motion that should describe the wave function in some semiclassical regime. And of course, I notice that phi is not necessarily real. If phi were a real function of x, then psi would have norm squared exactly equals to 1 as a function of x. But in general, of course, the probability density might be some function of x, so the phi will not be, in general, always real. Okay, so let's just go ahead and take this expression for phi in terms of psi and plug it into the form of the Schrödinger equation at the top of the page here and expand in powers of h bar. So what is the equation? Well, we have the second derivative of psi, which is the sum of two terms. So you'll have an I over h bar times the second derivative of phi, where prime denotes d by dx, minus phi prime over h bar squared. So the first term comes when the derivative hits the e to the I phi over h bar, brings down a phi prime, and then you take the derivative of the phi prime. The second term arises when you take two derivatives of e to the I phi over h bar, and then you have that p squared over h bar squared, just coming from the second term here. So that all has to be equal to 0. And when we expand in order terms of powers of h bar, what I mean is that we imagine that phi takes some value that is of order 1, plus a value that is of order 1 times order h bar, plus a value that's of order h bar squared, times something of order 1, and so on and so forth. And then we can go ahead and rewrite this equation for phi as an equation where we collect all of the like powers of h bar. So for example, the only expressions in this formula that are of order h bar squared involve phi naught squared plus p squared over h bar squared. So that's the order h bar squared in the equation for phi. Then there's something of order h bar. So what will you get if you look at this at order h bar? Well, you get an I phi naught double prime from this first term here. And then from the second term, you just need to take this expansion and plug it in and work out the term at order h bar. And that is going to be some sort of cross term where you have phi naught times phi 1, both primed, and with subleading powers of h bar. So if we wish to solve this equation order by order in h bar, that means that you need to set the separate powers of h bar in this equation all equal to 0. So, for example, phi naught will be determined by setting the term in this equation which has a 1 over h bar squared equals to 0. Phi 1 will be determined by solving the second equation with a power of 1 over h. Phi naught is determined by the 1 over h bar squared coefficient of this equation. Phi 1 is determined by the 1 over h bar coefficient of this equation, and so on and so forth. So from this equation, you see that phi naught prime squared is equal to p squared, or phi naught prime is equal to plus or minus p, or solving that equation implicitly, phi naught is the integral of p with respect to x. Here, let me write explicitly the dependence on x. And then phi 1 is determined by solving the equation that I phi naught double prime minus 2 phi 1 prime phi naught is equal to 0 or rewritten slightly, phi naught double prime over phi naught prime is equal to minus 2I times phi 1 prime. That's just this coefficient here. And then using the expression for phi naught above, where phi naught prime is equal to plus or minus p, we note that the left-hand side of this equation can be written as log of phi naught. Okay. We note that we can integrate both sides of this equation to find that log of phi naught prime is equal to minus 2I phi 1 plus a constant and since log of phi naught prime is just plus or minus the log of p, that implies that phi 1 is going to be I times the log of the square root of p, plus a constant. So taking this first equation and the second equation and plugging them into our expression for psi, which I remind you was e to the I phi over h bar, so that would be e to the I phi naught over h bar plus phi 1 plus dot dot dot, we see that the wave function, if I've done this all correctly, is going to be a constant divided by the square root of p, coming from the phi 1 term, times the exponential of plus or minus the integral of p. Plus, of course, higher order corrections. Any questions on this derivation? You guys have seen this before in principle? Maybe? Yes, question.
First, we're saying that we can write our log the wave function as a bunch of other functions turning power.
Yeah, all I'm doing here is writing an expansion for the wave function and powers of h bar. And one of the things that I am secretly thinking in the back of my mind is that I know that in a semi-classical limit, the wave function should be e to the I s classical over h bar, where s classical is something of order 1, has no h bars in it. So that is a hint to me that a useful way of organizing a perturbative expansion would be to first write down that classical term, which I've called phi naught here, and then understand the corrections to that classical term in a power series in h bar. So indeed, the next comment that I was going to make is that, in fact, what I called phi naught, which is this expression here, is very closely related to the classical action. So that's the next thing I was going to describe. But first, let me see if there are any questions. You guys have seen this derivation? Or you've seen something like it, if not exactly this derivation. Don't worry, you'll go through it again in much greater detail when you derive the next leading expression, the next correction to this in powers in h bar on the next problem set. Okay, so roughly, this equation can be understood as follows. So remember that in a semi-classical limit, the evolution of the wave function as a function of time, in the limit where h bar is very small compared to all other scales in the system, says that the wave function goes like e to the I over h bar times the classical action. Now, this is the wave function which is a solution of the time-dependent Schrodinger equation h bar d by dt of psi is equal to h psi. However, up here I wrote a solution to the time-independent Schrodinger equation where I was looking for a solution with fixed energy. And the relationship between them, of course, is that if you have a solution of the time-independent Schrodinger equation, i.e. an energy eigenstate, then that leads to something that evolves as in time with an e to the I over h bar times et. So if you want to compare our intuition, our semiclassical result for the solutions to the time-dependent Schrodinger equation to the time-independent Schrodinger equation, you have to add in that factor of et. So this is just a restatement of our earlier result that the semiclassical wave function is just the exponential of the classical action, just rewritten for solutions of the time-independent Schrodinger equation. Life would really be much easier if we didn't call both of those equations the Schrodinger equation. We should really call the time evolution one the Schrodinger equation and the other one the eigenvalue equation for H. Okay. So let's investigate that expression in a little bit more detail. So what is S classical? Well, it's the integral dt of the difference of the kinetic and potential energies. And what is E times T? Well, another name for it is the integral dt of the sum of the kinetic and potential energies. So the potential energies in this expression cancel, and using the fact that T is equal to 1 over 2m times, or using the fact that T is just equal to 2m times p squared, this is going to be the integral dt of p squared over m. And if we wish to compare this to our above expression for the WKB approximation, we can remember that p over m is the velocity dx over dt, so that one can change the variables in this integration and write this not as a t integral, but an x integral. So this would be the integral of p dx. So you see that what we have derived here, the WKB expansion, the WKB approximation, is really nothing more or nothing less than our old friend, the classical action, now rewritten in terms of a solution of the time-independent Schrodinger equation. And this coefficient here is the first non-trivial correction to this semiclassical result. Any questions so far? Yes?
Can you just repeat why you added dt?
Yeah, that's a subtle point. So remember, what is the thing that is semiclassically e to the I s classical? That's a solution of the time-dependent Schrodinger equation. That's a solution of the wave function as it evolves in time. Okay. What is the thing that I've written in the box up here? That's an energy eigenvalue. Okay. That's an energy eigenstate, the state where h psi is E psi. Okay. If you wish to compare the two, then you need to remember that if you're in an energy eigenstate, then you're not time independent. Rather, you evolve with a phase as a function of time. Okay. And that e to the I over h bar times et is that phase.
So you're just comparing.
Yeah, all I'm doing, I'm just comparing those two different equations. It's a little bit of I'm being a little sneaky here. Okay. I freely admit that. Okay, but at least it gives us an intuition for, you can write down formally this result, and it's correct, of course, but what I really want to convince you of, I left out an I over h bar. I'm disappointed that nobody corrected me on that. What you should really think of this is you should think of the quantity and the exponential as just the classical action, dressed up by a phase in order to make it a solution of the time independent Schrodinger equation. Indeed, in classical mechanics, we often give names to integrals of the form integral of p of x dx. The name we often give to it is the action. Okay. The word action is used in classical mechanics in slightly different senses sometimes. And sometimes we just give the name to that integral. We call it an action integral. Other questions? Okay. So, as always, whenever you make an approximation, the first question one should ask oneself is when the approximation is valid. So roughly speaking, so I remind you, okay, I've even rewritten it here, that this approximation says that psi goes like the exponential of I over h bar integral of p dx. Okay. So I can think of one case where this approximation is exact. And that's the case when the potential is equal to 0. Then p is just a constant. Remember, p is the square root of e minus v. So v is a constant, or v is equal to 0. Then p is just a constant. And this expression says that psi is going to go like e to the I p over h bar. That's a plane wave. Those are the solutions to the time-independent Schrodinger equation with no potential. So we know that this is an exact answer whenever the potential is a constant. So that means that this should be a good approximation whenever the potential is slowly varying in x. However, I would like to be a little more precise, because when I say that v is slowly varying in x, I need to say slowly varying compared to what? Okay, those words on their own don't have any physical meaning unless I say slowly varying compared to what. So let's try and understand more precisely when the WKB approximation is valid. So precisely, we expect that this approximation should be valid when the second term in the expansion of the equation of motion is much, much less than the first term. So let's look at this expansion of the equation of motion. So let's look at this term here and compare it to this term here. So if we just want an order of magnitude estimate of the size of these two different terms, we can just compare the size of this guy to the size of this guy. And so you see that the first term in the equation of motion will be much larger than the second term when that first term, phi naught prime squared over h bar squared, is much, much larger than phi naught double prime over h bar. And I've chosen to write it in terms of phi naught here rather than phi 1 because then I can just use the fact that, I can just rewrite this equation a little bit more simply. So it's h bar d by dx of 1 over phi naught prime, if I did that correctly, has to be much less than 1. Or, since phi naught prime is just equal to p, this is the statement that d by dx of h bar over p, which is h bar over the square root of 2m e minus v, is much, much less than 1. The advantage of thinking about things this way is that this is now an equation that is consistent with dimensional analysis. So that means that not only is it telling me that this is that the WKB approximation is good when v is slowly varying, but it's saying slowly varying compared to what? So, in particular, this is true. Well, first of all, if v is slowly varying, so that v prime of x is going to 0, then obviously this expression here is going to be much less than 1. If v prime is equal to 0, you're taking the derivative of a constant, which is 0. 0 is, it's a lot less than 1. Okay, but this also allows us to understand other circumstances when the WKB approximation is valid. Particularly when h bar is 0. If you fix the potential v, and then you take the limit where h bar is going to 0, then obviously the numerator goes to 0, and so the WKB approximation is good. Or, likewise, if you fixed v and h bar and took m to infinity, very, very heavy particle, then that's going to be well described by the WKB approximation. Or, fourthly, if you fixed h bar, m, and v and study energy eigenstates with a very large eigenvalue, then the denominator is going to be very big. And so, again, this approximation will be valid. So these circumstances are precisely when the semiclassical approximation is valid. So far in this course, schematically, I've talked about the semiclassical approximation as being an approximation where h bar is very small compared to all other scales in the problem that you are considering. And here, I've been able to make that a little bit more precise. So you see that even when h bar is finite, if you're studying energy eigenstates with a very, very large energy, then you can also think about them semiclassically. Or if you're considering potentials that are varying very slowly, or very heavy particles, you can also think about them semiclassically, even if h bar is not small. Questions? Okay. So let me just spend the next few minutes investigating in a bit more detail the implications of the WKB approximation. So first of all, the WKB expression for the wave function gives us a very nice way. So actually, let me write this as I over h bar times the integral square root of 2m e minus v gives us a very nice way of understanding the rough behavior of a wave function. So in particular, if you have some potential here, so let's say that this is v as a function of x, then you can see that if you're looking at the wave function at a place where e is bigger than v, then the argument of the exponential is going to be purely imaginary, and so the wave function oscillates. So if you have a wave function, if you're studying a state with energy E, then you know that the wave function is going to oscillate when E is bigger than V. And likewise, if E is less than V, you know that the argument of the exponential is going to be purely real. So it could either be e to the plus something or e to the minus something. And in order to have a normalizable wave function, at least for the sort of potential that I've drawn here, you know that it has to be dropping off exponentially rather than increasing exponentially, so that the wave function will look something like that. So if e is less than v, then the wave function is exponentially damped. And so this gives you at least a very approximate picture for what the solutions to the Schrödinger equation should look like inside some sort of arbitrary potential. And in fact, this picture can be used to understand a ton of physics. And so today, what I would like to do is use this to understand two things in particular. So first of all, I would like to understand the approximate quantization rule for energy eigenstates. And in particular, I'd like to derive the Bohr rule that angular momentum, for example, is quantized in units of h bar based on this WKB expression. And then later on, we'll use this to investigate tunneling, and we'll find that our results have a very interesting formal interpretation, which will come back and haunt us later on in the course. Questions? Okay. So, in order to understand the approximate quantization rule, I'd like to stare at this not very well drawn picture a little bit longer. Okay. So, remember that the WKB approximation is valid when the momentum p, which was the square root of 2m, E minus V, is very large. So if I have a potential of the sort that I have drawn for you, then in the interior here, P is going to be big if E minus V is large. And so the WKB approximation is good. But near a turning point, well, by definition, that's a place where E minus V is equal to 0, so that P is equal to 0, and so the WKB approximation is bad. So WKB is good when P is equal to 0. P is much bigger than 0, but it fails at the turning points where P is equal to 0. So, if you want to actually understand in more detail what the wave equation looks like for a bound state, then you actually need to understand the behavior beyond the WKB approximation near one of the turning points. Okay. So near a turning point...
Can I ask a question?
Yeah, sure.
Out near the turning points and past them, we never even satisfied any of the four requirements.
Oh, okay. Near the turning
why
point...
do we even... or past it, right?
Ah.
Okay.
Really?
Well,
Here, down here, P is, see, when I look at an approximation like this, what I really care about is the absolute value here, right?
okay.
So here, P, down here, P is large and imaginary, but the absolute value of P is much bigger than 0. So we expect that the WKB approximation should be good deep, well inside. So if I wanted to, this picture is getting a little crowded. So let me redraw that picture a little bit. So roughly speaking, you have some potential like this. Then the wave function looks like this. And you expect WKB to be good in that region. And it's the goodness of the WKB approximation in that region that will lead to the semiclassical Bohr quantization rule. And we also expect WKB to be good out here. And it's the goodness of the WKB approximation there that leads to our tunnel expressions for tunneling rates. And we expect WKB to fail near the turning points. Okay. Is that clear? Good. Okay. However, near a turning point, we could always take the potential and we could expand it in a Taylor series in powers of the distance from the turning point. And in particular, what one can do is use WKB far from turning points and solve the linear potential near the turning points and in order to obtain an approximate expression, one would then match these two solutions. Have you guys seen the solution to the Schrödinger equation when you have a linear potential? This is one of those classic examples that you often see in your first course in quantum mechanics. The solution to Schrödinger's equation with a linear potential, v proportional to x, is a special function known as an Airy function. Nothing particularly sophisticated about that problem. So I'm not going to bother to work out explicitly the solutions of the Schrödinger equation for a linear potential. They're Airy functions. They're some special functions. We could study it in more detail if we wanted to. Instead, what I'm going to do today is just proceed with the calculation pretending that the WKB approximation is good all the way to the turning points. And then that'll give us an answer that's close, but not exactly right. And then I'll just ask you to trust me when I tell you how that answer is modified by the inclusion of the matching to the Airy functions that one would use if one wanted to study the problem a little more carefully. So hopefully you find that reasonable. I hope so, because I certainly didn't prepare a lecture on Airy functions. Have you guys seen that, by the way? Raise your hand if you've seen an Airy function. Okay. So you guys have seen that more or less. So there's some straightforward way of constructing those solutions to the linear Schrödinger equation. So for the time being, let's pretend, we'll close our eyes and pretend, that WKB works all the way to the turning points. So, to be a little more explicit, we have some potential here, and we have, so there's the x-axis and there's v of x, and we have some energy, E, of the eigenstate, and then we have these two turning points that I'll call x1 and x2. And then the WKB approximation says that psi of x can be found by integrating I over h bar from x1 up to x. Okay. If you wish to determine psi of x at some intermediate point. However, the same WKB approximation says that the wave function could also be determined by integrating down from x2 instead of up from x1. That's just another version of the WKB approximation. And by equating these two expressions, we then obtain a constraint on the solutions to the time-independent Schrödinger equation. In order to understand this constraint, I'm going to use a particular fact, which is that it's possible to choose psi to be real. So that might look a little funny at first, because the way that I've written it, it apparently has a phase, which is oscillating. In order to see that, so in fact it turns out to be a general property of many quantum mechanical systems, that one can always choose the phase of the wave function so that psi, the solution of the time-independent Schrödinger equation, is always a real function of x. Why is that true? Well, here's a one-line proof of that fact. Well, psi of x is an energy eigenstate with a given value of E. E is real, and the Hamiltonian is a Hermitian operator. So if psi of x is a solution of is an energy eigenstate with a given value of energy, then so is psi star. And it has to have the same value of the energy. So those are energy eigenstates with the same value of E. So that means that they must be, if we assume the energy eigenstates are non-degenerate, then they must be related by a phase. And remember, they have to be related by an overall x-independent phase. So if psi and psi star are related by an overall x-independent phase, then that means that the real part of psi is also a solution to the Schrödinger equation with the same value of the energy. So let's just work with the real part of psi. That has to be an energy eigenstate. And so I am free to work with, to choose my overall phase multiplying the wave function so that psi of x is always real. In fact, this is not an accident. This is a consequence of one of the symmetries of the theory that we're studying. In particular, it's a consequence of one of the symmetries of one-dimensional particles moving in potentials. And so, as we will see later in this course, it is because this Hamiltonian is time reversal invariant. In particular, that the equations of motion don't change if I take t to minus t. And so we'll prove later in this course, in fact, you may prove it on a problem set, that whenever the Hamiltonian is time reversal invariant, it's possible to choose the energy eigenstates to be purely real. Okay, so if the energy eigenstates are purely real, those exponentials up here turn into cosines, because we're taking the real part. The real part of an exponential is a cosine. So what we have to do is we have to set a times the cosine of 1 over h bar, the integral from x1 up to x of p of x prime d of x prime, is b times the cosine 1 over h bar, integral from x2 down to x, p of x prime dx prime. So let's stare at that equation for a minute and think about how that could possibly be true. The only way that this can be true is if the arguments of the cosine differ by a multiple of pi. Because cosine is a periodic function with period 2 pi. But in fact, so you might naively think that the way that you could solve this is by saying that the arguments differ by a factor of 2 pi. But remember that cosine of pi and cosine of 0 are actually equal. They differ by a sign. And that's okay, because you can always pull an overall sine out of the cosine. So this can be solved only if the difference between these two terms, or the sum of those two terms, I guess I should say, namely the integral from x1 up to x2 of p, is equal to pi times an integer times h bar, in order to get the arguments of the cosine to work out. So this is the result that we derived, assuming that the WKB approximation was true all the way up to the turning points. If one were very bold, one can study this more precisely by treating the solution to the Schrodinger equation exactly near the turning points, by studying the Airy functions and then matching onto the WKB solutions. And the reason why I didn't do that is because it only gives a small difference to the result. In fact, it only says that we get an extra 1/2 there. I believe it's worked out in your textbook. I'm not sure, actually, but I think it is. So that's if we use Airy functions near the turning points. And n, of course, is an integer. So sometimes we rewrite this equation in a way that makes it slightly more suggestive in terms of our semi-classical intuition. So we can rewrite this as an equation where we integrate p from x1 up to x2 and then back down to x1 again. So that just differs by a factor of 2, of course. But where we now think of this as an integral over a whole cycle, a whole oscillation of the system where a particle goes from one turning point over, bounces off the side of the potential, and back again. And you will hopefully recognize this as the usual Bohr rule for the quantization condition for energy levels. And this equation is usually known as the Bohr-Sommerfeld Quantization rule. It leads to, among other things, the quantization of angular momentum in units of h bar. And it's really lovely because it allows us to develop a semi-classical intuition for the states of a quantum mechanical system. In particular, it tells us that semi-classically, the classical states, or the energy eigenstates, which determine the allowed energy levels, are those that enclose an integer, or I suppose I should say a half integer area of phase space as measured in units of h bar. So in particular, to understand why that's true, let's stare at this boxed equation for a minute. So let me rewrite it. So we have the integral of p dq, or p dx, is equal to 2 pi n plus 1/2 h bar, where n is some integer. So let's imagine that we have some classical system, and we can think of the phase space, the xp plane, So let me use x instead of q. And then if we have some potential that leads to some bound states, then the classical trajectories of the system will be some curves in the xp plane, and those curves will have some complicated shape depending on the details of the potential. But if the potential goes to infinity, x goes to plus or minus infinity, then the particle will always bounce around inside the potential, meaning that the paths in phase space will always be closed loops that come back to themselves. And of course, the equation for that closed loop is just the equation for the conservation of energy. These closed loops are defined by labeling by their values of the energy. So these paths through phase space at least for a one-dimensional particle, are labeled by energy. And then the allowed energy levels are precisely those where the area enclosed by this loop is a multiple of 2 pi times h bar, maybe times a half integer. Because, as you can see, the left-hand side of this equation is nothing more and nothing less than the area of the loop enclosed by the loop through phase space. And so this leads us to a very interesting way of thinking about quantum mechanics, namely that in quantum mechanics, we have one state per Planck area, per Planck area in phase space. If you want to think about quantum mechanics semi-classically, you should think of the phase space of your system, the XP plane, and you should think of dividing it up into little cells, each of which have area h bar. And each one of those cells will give you a quantum state. Now that's only a rough picture because we're only using some approximate notion, but at the very least it tells you an easy way of estimating the number of quantum states of the system. If I hand you a classical system and I say, estimate the dimension of the Hilbert space of this classical system, then the answer is, semi-classically, it is the volume of the phase space measured in units of h bar. I should make one comment here, which is a comment about dimensional analysis. So phase space is the XP plane, which means that areas in phase space have dimensions of x times p. And so in order to measure their areas, we have to measure them in some units, and you have to measure them in some units of some quantity that has dimensions of length times momentum. And h bar can be regarded as the fundamental unit of area in phase space. When understanding semi-classical limits of quantum mechanics, it's always important to think about the dimensionful quantities under consideration. And h bar has a particular set of units. One of the things it has units of, it has units of action, Lagrangian times time, energy times time. And so that means that you can regard quantum mechanics as a statement about action integrals being quantized. But h bar also has units of length times momentum, which means you can think about quantum mechanics as a quantization of areas in phase space. And here I've talked about a one-dimensional system where the phase space is two-dimensional. But, of course, one can generalize this to higher dimensions. For a particle moving in 2 dimensions, the phase space would be 4-dimensional. And then I think about the quantum states as 4-dimensional cells of 4-dimensional volume, that is an integer in units of h bar, and so on and so forth. Are there any questions about this? Hopefully, this is not completely new to you. I mean, I assume that you have seen the Bohr quantization rule before, but I don't know whether you've seen it really thought of as a formula regarding the quantization of phase space. Yes?
When you give an example of two variables, it tells that units of h bar squared.
Exactly. Right? Just by dimensional analysis, if you are measuring the volume of cells in phase space for a two-dimensional particle, the cells are 4 volumes, which have dimensions of length squared times momentum squared. And just by dimensional analysis, the only way that I can measure their dimensions is by dividing it by something with the same dimension, which would be h bar squared. Okay. So to say that another way, the dimension of the Hilbert space of a quantum system is roughly the volume of phase space in units of h bar. And this is a little piece of lore. It's a little slogan that is a great way of making contact between quantum mechanical notions and classical notions. Okay. Even if you don't understand the Hamiltonians of some system or the dynamics in some complicated way, you have no idea how to construct the Hilbert space precisely. If I hand you a classical system, you can always estimate the dimension of the Hilbert space by counting the area of the phase space and dividing by the appropriate units of h bar. Now, usually for a particle in an infinite space, the phase space is, of course, infinite area or infinite volume. A plane has infinite area. But, for example, if you want to say, I want to estimate the number of states or the dimension of the Hilbert space describing states with energy less than a given value, what do? You draw the curve of constant energy on the xp plane, and you calculate the area inside it. Or if you're looking at a particle in 2 dimensions, you draw the 3-dimensional surface of constant area, and you calculate the 4 volume inside that surface. Divide by the appropriate units of h bar. So is this concept new to you? I never quite know whether this is incredibly basic and something you guys already know and have seen before, or if it's something totally new. How many have you guys seen that before? The statement about unit areas in phase space? No. Okay. I'm glad I spent at least a few minutes on it. Yes, there's a question in the back? No, you were just raising your hand because I asked you to. Good. Any questions? I should point out, of course, that the Bohr-Sommerfeld rule is just an approximation. But in fact, Bohr-Sommerfeld is exact, and we can easily guess for which systems it is exact. It is exact for precisely those systems where the path integral approximation in the stationary phase limit was exact, because it's very closely related. In particular, it's exact for the simple harmonic oscillator. Okay. For the simple harmonic oscillator, the curves of constant energy in phase space are just ellipses or circles, and one can calculate their area, calculate the quantization rule, and you'll get exactly the quantization of the energy spectrum that we derived exactly last class. So, the WKB approximation is also useful if we want to understand tunneling. So up above, previously, I was imagining a case where we were using WKB when the energy was greater than potential. Let's imagine that we have the following situation. We have a particle which is trapped up here in the local minimum of a potential, and we want to estimate the probability that it will tunnel quantum mechanically into the global minimum. So it has to tunnel through this potential barrier. So, again, I could use the WKB approximation to compare the values of the wave function on either side of this potential barrier. And again, the WKB approximation will fail very close to the turning points. But I will just assume that it's good even up to the turning points, and admit to myself that that might be only an approximation, and an approximation that could be improved by considering matching onto the Airy functions, again, that describe the exact solutions of a linear potential. But in the approximation where I neglect that correction, the WKB approximation then allows me to estimate the tunneling probability just by using the fact that when E is less than V, E minus V is negative, so the quantity in the square root is purely imaginary. And so this is some factor that I'll call E to minus gamma over 2, where gamma is 2 over h bar times the integral from x1 up to x2 of the square root of 2m, now times v minus e, in order to make it positive. And so that the tunneling probability is the square of the wave function so that would go like e to the minus gamma. Now, this has been a bit of a schematic estimate. In fact, there's one thing about this statement which obviously makes no sense whatsoever. Okay. So if the particle is in a potential, in an unstable local minimum of the potential, sorry, that's an awfully sharp global minimum, then of course the tunneling probability is 1 if you integrate over all time. So when I say tunneling probability, I really mean tunneling probability per unit time. Now, if you look at this expression, tunneling probability per unit time goes like e to the minus gamma, then there's something not quite right about that, because e to the minus gamma is dimensionless, and a tunneling probability per unit time has dimensions of 1 over time. And so one actually needs to improve this estimate in order to get something with the correct units of dimension. So, for example, one could make a more refined estimate by, for example, well, if you just want to do a sort of back-of-the-hand estimate, one thing you could do is you could calculate the amount of time it takes for the particle to start at one side, for example, to start at the turning point, get to the other side of the potential, and bounce back again, sort of to go along that trajectory. And then that, in fact, would give you something with the correct dimensions, which would you would multiply by this exponential in order to get the appropriate tunneling rate per unit time. So that's just some sort of semi-classical estimate. But if one were bold, one could go ahead and soup that up a little bit by saying more formal things about the WKB approximation. But for the purposes of rough estimates, at the very least, these exponentials that we're discussing are much bigger than any of the prefactors that we would discuss. And so for many purposes, you can just forget about those prefactors and declare that the tunneling probability goes like e to the minus gamma, where gamma is the integral under the potential of the square root of v. So it's an integral through the potential barrier. So this is an integral across the potential barrier. And from this expression, you can see that if you have a very big potential barrier, then tunneling is going to be very unlikely. And if you have a very small potential barrier, then tunneling is going to be very likely. And so, for example, and this is in fact an exercise that I do think you're going to do next time, one can use this to estimate the probability for an electron to escape a nucleus via beta decay, where you just imagine that the neutrons in the nucleus are actually bound states of protons and electrons, and this is going to be some unstable configuration because the electron is allowed to, could in principle be out at infinity, very far away from the proton to which it's bound, but there's some potential barrier preventing that, and if one models this potential barrier, one can estimate the decay rate of a nucleus via this decay process. Yes?
Could you measure a particle's momentum while it's tunneling?
You could measure its momentum after it's tunneled, and then use conservation of momentum to infer its momentum before it tunneled.
But while it's tunneling? Would be-
I mean, it's hard for me to imagine how one would do that in practice, but
Is there anything to measure?
you could certainly, well, you could measure the decay rate due to beta decay of some nucleus. Okay. So you can measure tunneling. Tunneling is something that we see in nature. It's responsible for all radioactive decay, essentially. For example, you could imagine, let's put it this way. If you had a particle trapped in this potential, you could measure its position. And you might get very, very lucky and see that its position is underneath the potential barrier. But you wouldn't, of course, if you measure its position exactly, you wouldn't be able to determine the momentum of the particle exactly. That's on the uncertainty rule. Instead, there would be some, if you declare that you're going to measure the position of the particle only very roughly, but let's say finely enough that you can decide whether it's under the potential barrier, then you could also measure the momentum of the particle at the same time. Again, only very roughly. Any other questions? Yes.
What's the potential in this case?
Oh, for the nucleus via beta decay? There's some model for the potential. So there's a rather famous formula that you're going to derive, which is known as Gamau's formula for the probability of nuclear decay. And roughly speaking, I don't actually remember the detailed form, but roughly speaking, it's something like, well, what does it look like? Well, the potential, you just approximate it by some square well. So, far away it falls off like 1 over r, okay, because of the electrostatic repulsion. And then you just approximate it by some square well, because, at the time they didn't know anything about the nuclear forces. So they just approximated it by some square well, and they said, well, the electron has some energy, and so it's possible to tunnel through here. And I don't remember actually if they declare that there's some additional tunneling barrier. Yeah, I don't remember the details, but that's the basic idea. You'll find out all the details. Okay. Other questions? Have you guys seen this formula before for tunneling probabilities? Yeah? Everyone? Just 1 or 2 people? Okay. I see mystified expressions, which makes me feel like it's good that I went over it. Okay. I have 10 minutes left, so now let's really mystify you. Okay. This is awesome. The WKB approximation for E greater than V can be interpreted, maybe the 2 T's, or maybe 1 T, I don't remember, as a classical path. You can think of a particle bouncing back and forth between the walls of potential. However, what about tunneling? In this case, E is less than V, and we've seen that the wave function decays exponentially. But the equations are so similar that you might wonder whether there is a no interpretation of the particle is moving on a classical path. even though it's on a trajectory that's not allowed by classical mechanics. It's not allowed by energy conservation. And the answer is that this now has an interpretation as a classical path, but a classical path of a different theory. And in particular, it's a theory with imaginary time. Let's understand that. So, let's consider the dynamics of a particle in what is known as Euclidean space, where I take the normal time coordinate of quantum mechanics, and I declare that instead of it being real, it is purely imaginary. And so I'll write it as I times t sub e, where t sub e stands for Euclidean time. Why do I say that this is a particle in Euclidean space? Well, I call it Euclidean space because when t is purely imaginary, that means that the invariant interval of special relativity so the invariant interval between two events is x squared minus t squared becomes, when t is purely imaginary, the usual expression for the length between 2 points in Euclidean geometry. So, very often, when you consider more sophisticated applications of quantum mechanics, you will see that formulating classical dynamics, but classical dynamics in terms of an imaginary time variable, is often very useful for understanding quantum tunneling processes. And in fact, it's also very useful for understanding all sorts of other processes, as we'll discover later on in this course. So, why is this useful? Well, let's remember that the action of a particle is the integral of 1/2 m x dot squared minus v. Or, if I were to write this in terms of the Euclidean time variable, this would be minus I times the integral dt of 1/2m dx by dt Euclidean squared. Sorry, I should write this a little, I should not skip quite as many steps. So, if I just want to take t to t Euclidean, that will give me a minus sign in this first term here, which will give me that overall minus sign out front. And then, if I want to change the measure to write this in terms of t Euclidean, dt is I times t Euclidean, so I get a minus I. So that means that the exponential factor that appears in the wave function in the semiclassical limit is 1/h bar times the Euclidean action (1/2m) times dx now by dt Euclidean squared plus v. And just as in normal mechanics, I can find a classical path by extremizing the usual action. I can now find a classical path through Euclidean space by extremizing the Euclidean action. And the Euclidean action is identical to the usual action, except for an overall coefficient out front, which doesn't change the equations of motion, and for the fact that the potential has changed sign. So, what is this teaching you? This is teaching you that if you have a classical problem with a potential that looks like this, and you have some energy, and you want to understand the tunneling through the barrier, then in Euclidean signature, what you do is you turn this potential upside down, and you look at the classical path between those 2 points. So now, because the potential has been turned upside down, a path that was forbidden is now allowed, and the paths that were allowed are now forbidden by classical mechanics. And indeed, we can now use this to check that this reproduces precisely the tunneling probability that I derived for you using the WKB approximation. So the equation of motion in Euclidean signature is now not, so the usual equation of motion would say that the second derivative of x with respect to time is minus v prime, but now, because we've changed the sign of the potential, it's plus v prime, and there is a conserved quantity associated with that equation, which is the energy, which is now not T minus v, plus V, but is T minus V. So that the momentum P, which is mx dot, is, by this equation for E, just the square root 2m times v minus e. Or, okay, so let's just say that the energy is equal to 0 for the trajectory that I'm studying, so then P will just be the square root of 2mv. So that Is over h bar, using this formula up here, is 1 over h bar times the Euclidean action, which is 1 over h bar times the integral dt Euclidean of, well, the kinetic energy plus the potential energy, 1/2 the kinetic energy plus the potential energy, which is just m times dx by dt Euclidean squared, using this equation of conservation of energy, or using the same argument that we went through earlier, I over h bar times the integral of p squared over m dt Euclidean, or just p of x dx. Now integrated under the potential barrier. So from under the barrier. So what does all of this mean? This means that if you want to look for a quantum instability of a system, what we need to do is find solutions to the classical equations of motion with purely imaginary time. And then the tunneling probability is the exponential of minus 1 over h bar times the action of this classical solution with purely imaginary time. And this is referred to as the Euclidean time formalism, or the imaginary time formalism. At this point, you can view this purely as some sort of formal trick for manipulating the equations of motion in order to give you an approximate expression for a tunneling probability. But when we study quantum statistical mechanics, we'll see that in fact this Euclidean time formulation actually leads to a rather deep relationship between the ideas of unitary time evolution that we studied in the last 2 weeks and ideas in finite temperature physics. So I realize that my comments in the last 10 to 15 minutes or so have probably been rather mysterious, and this is certainly not something that I expect that you have seen before. But I feel like it's something I want to introduce, at least briefly, because it is a formalism and a way of thinking about tunneling that does show up in a lot of places in physics. I'm out of time here, so maybe if you have questions, you can ask me after class, or next time when we start with quantum stat math.